Hey everybody, in this video we are going to do the fourth and final exercise related to our East Texas model. And in this case we're going to do a number of things to our model. We are going to import a polygon representing the outline of this landfill, and then we're going to adjust the recharge in that part of the landfill so that later when this model is used for particle tracking and contaminant transport analysis, it has the right flow conditions based on the amount of leachate coming out of that landfill. And we're also going to play with our hydraulic conductivity values. And then finally, we are going to make some changes to how we simulate this well on the right, specifically how we allocate the flow rate between multiple layers, and we're going to use one of the advanced well packages to do that. So, as was the case with the other exercises, we downloaded the associated zip archive and unzipped it, and that is modf map 4. So we'll open that up, and here's our solution from the previous exercise, part 3. And we'll do file save as and save this as East Texas 4.gpr. Okay, what are we going to do first here? Let me scroll down. And first thing we're going to do is we are going to create a recharge polygon right here for the landfill. Now again, we've designated a uniform recharge over the site, and that's fine, and we're going, but the objective, the longer term objective, is to use this model to simulate how the leachate leaking from the bottom of this proposed landfill would potentially be transported by the groundwater. And it's probably not going to make a big difference, but it would help to reduce the recharge over the landfill. The landfill presumably would be capped and would have a liner on the bottom, so you're not going to get the same recharge as you do in the surrounding material. The recharge rate that you would have coming out would be whatever the leakage rate is out of the landfill, and which would be a much smaller amount. And so to do that, we need to modify our recharge coverage to include a rectangular polygon here. Now we could, in earlier versions of this tutorial, you'd click on 4 points and then edit the coordinates. Another way to do that is if you have the polygon representing the landfill as either a CAD file or a shape file, you can import it and you don't have to digitize its coordinates. That's especially helpful if you have a complex boundary. And so we are going to go to the GIS module right here. It's just to the right of the map module, and we're going to say add shapefile data, and it says landfillarcs.shp. So this is a shapefile that has those arcs, and now they're sitting down here as a generic GIS layer. Now you can import shapefiles and just use them as like a base map in the background. But another thing you can do, notice I have the recharge coverage selected here. Now if I right click on this and I say join, let's see, where's my GIS shapes to I need to do it up here, GIS shapes to feature objects. Here we go. What this command does is it takes the shapes in this shapefile and it converts them to feature objects in the map module, and it'll add them to whatever coverage that you have active. And actually it lets you pick which coverage you want, which is nice. And then I'll click next. And I'll say, let's map this to the elevation. Now what this allows you to do, if you have an attribute table associated with your shapefile, you can convert the properties on that attribute table to columns in your attribute table and your feature objects, and that can be really useful when you're importing not just geometry but data. In this case, we're just importing geometry, so we're just going to do next and finish. And now if I turn this off, let's see, you will see that rectangle right there is now a set of arcs in this recharge polygon. Now remember, our recharge polygon was originally a single polygon that goes all the way over this domain. And so if I go here and I do select polygons, it's the entire thing. So what we need to do is go to the feature objects menu and run build polygons again. And now it splits this into two polygons. So we have this polygon with the original recharge rate, and this polygon with the original recharge rate. Now what we're going to do is we are going to reduce that by a factor of 5. So I'm going to change it from 0.003 to 0.00006. So that's 1/5 of the original recharge rate, and that would represent the leakage rate of our leachate coming out the bottom. Okay, so we'll click save on that, and we'll map that over to ModFlow in a minute. And the next thing we're going to do, we're going to go back to our Aquifer properties. We have these two coverages, Aquifer Layer 1 and Aquifer Layer 2, and they allow us to input our hydraulic conductivity. Now, one thing that we ignored in our first model is our vertical hydraulic conductivity, which, as you may recall, in the LPF package, you can define your vertical hydraulic conductivity one of two ways. You can explicitly define it, or you can enter a vertical anisotropy. The vertical anisotropy by default is 1. So we didn't change it in part 3, so we had the vertical K was equal to the horizontal K, but that's generally not the case. So in this case, we want to specify our vertical anisotropy. And let's double click on this. So we're going to enter a vertical anisotropy of 4. And what that means is the horizontal K is 4 times greater than the vertical K. So to get the vertical K, you would take 5.5 and divide it by 4. And so that will be a more realistic value. And now let's go to our layer 2 polygon, and we'll turn on vertical anisotropy. And we'll double click on that. And you know, in my previous video I changed this to 2, but it's supposed to be 10. And we'll change this to 4 now. We notice our bottom layer is 10 and our upper layer is 5.5. Generally, your lower layers have a lower hydraulic conductivity, but not always. It's possible to have a coarser grain material at a lower depth. And so that's what we have in this case. And so now, with those two changes, we could say map to ModFlow. And we could run our model again, and let's see, save that again and read in our solution. And now you notice the contours changed a little bit. So by changing that wasn't, I mean, there was a little bit of impact from a reduced recharge in the landfill here, but also having a lower value of vertical hydraulic conductivity will change the distribution of your heads as well. So there are a couple reasons we saw the heads change. Now, for our last part, we are going to change how we simulated this well over here. Now, in the last video, the first time we ran the model, the well was in the first layer, and then we put it in the second layer, and then we used the layer range option to have it both in the first and the second layer. But when we did that, we noted that it put the full pumping rate in both layers, so we went in and kind of manually partitioned that pumping rate of -300 between the two layers. Another way to do that is if you go into the let's see, Gotta get the right tool here. If you go into the well properties, instead of going from layer 1 to 2, if you turn on a screen and have it go from, say, 190 to 160, so you use a screen with this one has a 30-meter screened interval. It ignores your layer assignments and it uses those screen elevations to partition the flow. And so when I say map to mod flow now, and now if we go in and look at the well package, you will see that well number 2, it's partitioned 119 and 180. So it's partitioned the flow between those two layers based on how thick the layers are and based on the hydraulic conductivity and based kind of on the transmissivity. Now, in reality, that's not, I mean, that gives you a good estimate to how the flow is partitioned, but it's not as accurate as it should be. Ideally, what you do is you run the model, and the amount of water that's partitioned that comes from each layer should be a function of the heads and the pressures in each layer. And it's something you really shouldn't, you don't know how it's partitioned until you actually run the model. And so for this reason, they developed some subsequent well packages in ModFlow called multi-node well, MNW, and there are some different versions of that. And so let's experiment with the MNW package. So let's go into the coverage setup, and instead of using wells, we don't need layer range anymore. We're going to use the MNW2 package, which is the most recent iteration of that. And then we are going to double click on that well. So now we've got a whole bunch of extra properties that we can enter for a well. It's kind of ridiculous how many there are. And so there's just this is used to do a really accurate representation of the flow into wells and how it's partitioned, and you can have instead of specifying the pumping rate, you can specify the flow rate if you want, and so there are a lot of different options. So we are going to specify our pumping rate, so we're going to go over until we find there's a property called QDES. Where is it? Let's see. Oh, here's the problem. I need to change its type to MNW2. Okay, that's the first thing we got to do. Sorry about that. And then if we scroll over, we should find a QDES. And I'll be darned, I can't find that. Q design. Oh, there it is. I'm just blind. It's the first one on the list. Sorry about that. Minus 300. There we go. I thought I was going crazy there. Skipped right past it. For some reason, I thought it was farther to the right. Okay, and then in the loss type, we are going to use the time equation. And this controls how the head losses occur in the vicinity of the well. And then we're going to click on this bore line button, and that should bring up boy, I'm going crazy here today. I can't bring up this should bring up a table dialog. Okay, I paused it for a second and I figured out the problem. The reason I couldn't bring this up is I had the use screen interval on, and if that's on, it won't let you click on this button, so I had to turn that off. And then basically it brings up this little bore line. So what this allows you to do is put in a well screen and some properties associated with the well screen. And so in the screen begin, we're going to do 180, and the screen end, we're going to do 165. So very similar options, the elevations that we had before. Now this is the radius of the well, and that's going to be 0.05, so 5/100ths of a meter. And the rest of this we can just ignore. So that's our bore line. And yeah, that should be everything we need. So just a cute is, so what we entered, we turned off the use screen, which we had on before. Changed the type to MNW2, changed the design flow to -300. Now notice this is design flow. It may or may not reach that full pumping rate. And then the bore line just allows you to give you know, top and bottom elevation for your well. Now why is that? Seems to have lost the values I just entered, so let me enter that again. 180, 165, and 0.05. Let's see if that, okay, now we got it. I'm glad I checked that again. Maybe I hit the cancel button or something. And we have the lost type of time. So there we go. And let's save our changes. Now there's one other option that we want to explore here, and that is so we have this raster here representing the ground surface that we used last time. And remember, we had these drains that we assigned in part 2, and we gave it a beginning elevation and an ending elevation. Well, these presumably represent these ravines that are, they should be represented, the geometry of those should be defined by this DEM. So rather than just doing an elevation at the top, an elevation at the bottom, have it linearly interpolate, it can be more accurate to just derive those drain elevations from your DEM. And so the way you do that is we go to the drains package, and we're going to use the select point node tool, and we're going to select all 6 of those nodes and bring up the attribute table, and we'll say we just want to look at the drains here. And then up here at the top there's a little pull down button, and we want to select raster. And then there's only one raster in memory, so we're going to grab that. And by doing that, that marks all of these as being interpolated from a raster. Now, if the 2 endpoints come from a raster, then the entire set of elevations along the length of the drain will come from that raster. And so let's do map to mod flow. And those drain elevations now should be mapped from that. We should have in the packages, we should have the MNW2 package defined for us. Looks correct. And we have this, we're still using the well package for this one over here. So we have the regular well package here and the MNW package here. And so let's check simulation, make sure we don't have any errors. I got that same cell size warning we got before. We're going to ignore that. And here we go. And so now we let's go ahead and look at our flow budget. So the wells -349,999. So yeah, pretty close. Not exactly 350, but for all intents and purposes, that's exactly 350. Now here's something interesting. You'll notice that before we had 0 water going out through the drains, and I think the drain elevations were too high. So in this case, we have a drain elevation of, or excuse me, we have 198 cubic meters per day discharging through the drains. So by switching that to the, so that it gets its elevations from the rasters, I think we have a more accurate drain here. And so that makes it work out a lot better. And then let's see, let's zoom in on our well here. And let me change the display options here. Let's go to the 3D grid, turn off the cell edges, let's turn on color fill and linear. And now this is layer 1 and this is layer 2. So you can see a little bit different distribution of heads in each of those layers. And you know, if we wanted to, we could see how much of the let's go in and do a little zone budgeting here. I'm going to select the cell containing that. Well, let me just select that entire set of cells. Let's see, I need to turn the cell edges back on before I can select cells. That's right, or before I can see the selection. There we go. So I'm going to select that cell right there, double click on it, and I'm going to say that is zone budget 2. And so let's see, now if I go to my flow budget dialog and I say this for wells in zone 1, let's see, wells in zone MNW zone 2. Let's see, I need to maybe unselect the cells. Try that again, flow budget. Oh, there we go. Now zones, zone 1, zone 2. Okay. Here we go, out, MNW. 171. So for zone 2 we have 171. Going out in zone 1 we have 128. So that tells you how much partitioning you have between the MNW well in layer 1 versus layer 2. So 128 in layer 1 and 171 in layer 2. So together that adds up to about you know, minus 300 pumping rate. So that is the best way to represent wells that span multiple layers. We were able to get a more accurate or a better usage of our drains by using the DEM elevations, and we designated a reduced value of recharge in this polygon, and I don't think we ever verified that. So let's go over. This is about let's see, row 152, 153. So if we go double click on our recharge package array, scroll over to about 153 and go down, you'll see this big region in here where the recharge is reduced to 0.0006. And so anyway, that completes our 4 tutorials on using the conceptual model approach to build this model in East Texas. We started with something really simple and gradually added complexity, and hopefully along the way we learned some really nice tricks about using the conceptual model approach.